Welcome back my dear students. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3, which is data analysis and decision making 3 lecture series under NPTEL MOOC. And this total course as it is a third part of the DADM series is for 12 weeks. Contact hours is 30, which when split over the number of lectures is 60 in number, and each lecture is for half an hour. So, and in a week we have 5 lectures. So, after each week we have one examination, small assignments, and after the whole course is over there is one final examinations. And as you can see from the slide, we are in the 34th lecture, that means we are in the 7th week, and with the end of the 34th and then 35th you will basically have the 7th assignment. In totality, as you know, there are 12 weeks. So, you will have 12 assignments. So, we were discussing about the concept of this epsilon amount being added for the case of the transposition problem, considering that degeneracy is not to be there, and once degeneracy is removed, obviously you will move back to the concept of trying to find out the optimum feasible solution by moving along the corner points. What you do in the linear programming is the same thing, like shifting delta amounts you will basically create, trying to move from one of the corner points, feasible corner points, to the other feasible corner point, basic considering that you are starting a basic feasible solution till we lead the optimum point, which is in this case is the minimization problem. So, here you consider in the northwest corner method that the degeneracies are, if they are there, you will basically add and subtract delta amount in each cells accordingly, such that you reach the concept of optimality. Now, for the transposition problem, we will come back to the transposition problem later on, considering the sensitivity analysis. If you remember the sensitivity analysis which we considered for the perturbations of the constraints. Here I will discuss later on in this 34th and the 35th class some concepts about the DA method. And why DA method? Because even though it looks nonlinear, we will consider linear simple solution methods, like as we did in the linear programming for the DA method. This DA method was considered in some detail in DADM2, but I will go into the details, because if you remember, I do remember quite vividly that I did mention that DA method, which is data and envelope analysis method, would be considered in DADM3 in details, considering the solution methodologies we have already discussed, which is the linear programming. So, in the optimum solution problem for the, so I will come to that DA method later on, but in the optimum problem solution, considering that you have the destinations given as D1 to D4, origins as given as O1 to O3, and your total cost structure is given as shown in the matrix. So, the cost are C11 is 1, C12 is 2, C13 is 3, C14 is 4 in units, and the corresponding values for transporting from O2 or getting products as D1, D2, D3, D4, which is basically the values given in the second cell would be, second row would be 4, 3, 3, 0. So, remember this 0 cost basically means that whatever transportation you do between O2 and D4, the total cost component per unit is 0. So, obviously, the total amount which you will transfer will have a 0 cost, but obviously that it would not be 0 always. In the sense, the total cost would not be 0 always for the whole structure, because you cannot transport more than the requirement, or you cannot transport more than what is being supplied from either the origins or the destinations. And similarly, for the third row, the values are 0, 2 to 1, which would basically again mean the 0 cost is the cost concept which is there between O3 and D1, and the other values of the cost functions are 2 to 1. And if I look at the marginal values which are basically the corresponding total values of AIs and AJs or BIs, depending on how you have been able to nomenclature the values of A's and B's. So, if you are considering the number of origins from where you are transporting, the warehouses from where you are transporting, or the factories from where you are producing and then transporting, they would be basically given by the nomenclature I is equal to 1 to m. And if you are considering the retailers or the end customer who are there, they will be n in number and they will be marked by j is equal to 1 to n. The values are on the rightmost column is 6, 8, 10 and the total is 24. Similarly, if I consider the overall values which is given for D1, D2, D3, D4, they are 4, 6, 8, 6. So, the total is also 24. Now, if I consider the simple northwest corner method solution, so the values which comes out to be are 4, 2 from O1 to D1 and O1 to D2. So, the total cost on the right hand side, no total transportation on the right hand side is 6. If I consider O2, so I will transport as per the northwest corner method, I will transport to D2 4 and to D3 4. So, the total is 8. I am basically counting the rows, the values. If I transport products from O3 and D3, if I see the values is 4 and 6, so again the total value is 10. So, the right hand side balances. If I consider the column wise, the values are 4 along the column. So, it is 4 here. So, I will use a different color concept. It is 2 and 4 from O1 to D2 and O2 to D2, it is 6. If I consider the next quantum is O2 to D3 and O3 to D3, it is 8, and the values if I transport from O3 to D4, it is 6. So, again the total value comes out to be 24. So, hence the total cost would be corresponding to the fact by the total quantum into the per unit cost. So, it will be 4 into 1 plus 2 into 2 plus 4 into 3. So, 4 into 1 is 4, 2 into 2 is 4, 4 into 3 is 12, 4 into 3 is 12, 4 into 2 is 8, 6 into 1 is 6 and the total cost is 46. Now, if I consider the values optimum solution values, if I perturbed, the perturbation values would be such that the total cost component in the rows or the columns remains as it is given as 6, 8, 10 along the rightmost column and the values being 4, 6, 8, 6 in the bottommost rows. So, perturbations would basically mean that the values of q which you are going to consider, we have to basically find at each step, but the values would not be violating the constraints which are there. That means, the summation of each row is equal to b values which are there on the right hand side and summation of each values along the columns would be equal to a value. So, a and b are just the nomenclature which I am giving and the total sum of a's or and the is equal should be exactly equal to the total sum of b. So, the total quantum of goods which is being marketed or shipped from all the factories combined should be exactly equal to the total amount of demand which is being demanded at the retailers or the warehouses. So, consider I am trying to transfer from the factories to the warehouses. So, a perturbation values as we change the total cost structure considering the epsilon methods which we have. So, if we keep changing the values in a cyclic manner, considering that the constraints are met along the rows and along the columns, then the total cost structure now would become, if I consider, is 6 between O1 and D2. So, I will write the cost, it will be easier. 1, 2, 3, 4, I will write it 1, 2, 3, 4, 4, 3, 3, 0, 1, 2, 3, 4, 1, 2, I should use a different color. So, it should be easier. One, 2, 3, 4, these are the unit costs. 4330 and the last row values are 0, 2 to 1. So, now let us see what are the costs and highlight what are the values are. So, I use the highlighting on. So, 6 0 is 12, then 8 3 is 24, 12 and 24. So, I will keep writing it also. So, 12 is the cost, 24 is the cost, 6 is the cost, 0 is the cost. So, I highlight the values. So, the total cost is 12 plus 24 is 36, 36 plus 6 is 42, and obviously this is 0. So, if I see the values here, sorry, they were 46. So, I have been able to transfer all the amount of goods between origin and destination. Total cost comes out to be, if I add them up, so which is 4 unit less, and it can be improved accordingly depending on the problems. Now, before I come to the data analysis, which I did discuss in DADM 2, and what was the significance which I mentioned about the optimization from the simple linear programming concept. So, first I will discuss something about the loss functions. So, loss functions are generally very heavily used and quite important when you are considering the concept of optimization, or also in the concept of estimation, which is basically from the point of view of statistics and probability. Now, what do we mean by loss? Loss means that you have something to predict, something to find out, and if you are not able to predict to the exact value, you have some differences. So, if there are differences, obviously you will entail some costs. If they are costs, you will want to basically find out that what is the overall accumulated cost which you will have, based on which you will try to basically minimize your total optimum value, whether it is a maximization or minimization. We will be considering the minimization problems only, and it can be done for the maximization problem also, but we will consider the negative sign accordingly. So, whenever you are doing any statistical and estimation problem and observations are there, you collect the observations which you call a sample. And why do you need a sample? Because there is a population has some parameter values, which we know in a distribution the parameter values are scale, shape and location, which will generally denote by alpha, beta and gamma. These are the symbols, and we need to basically find out the scale, shape and location parameter, because based on that we will be able to find out what is the first moment, what is the second moment, and so on and so forth. Because in generally for the case of the normal distribution, you have mu and sigma square. In the case of exponential distribution, we will have only one parameter. If it is basically a exponential distribution which is shifted onto the right, we will basically have a 2 parameter exponential distribution. Similarly, we can have a beta distribution of 3 parameters and so on and so forth. Now, whenever you find out a sample, as I was saying, and our main interest to basically study some characteristics of the population, and if the population is not known in all the parameter values, we have to take a sample in order to basically find out some characteristics of the population by using the estimates in the sample. And there are different type of studies which can be done, but our main concern would be when you are taking a sample or the set of observations from the sample, those should be chosen in such a way and be combined, the combination should be done in such a way to calculate the best estimate of the population parameter such that the error is minimized. So, what is the error? That would basically come out in different situations. So, whenever you are collecting a sample pertaining to data set, you will basically consider that there is a realization of those values, and I have already discussed that in DADM 1. So, there is a realization of those values. The realization of the values means that there is a random variable. When you basically read it, we are trying to understand that the actual value based on which you will try to predict or forecast would be the realized value. So, say for example, there is a dice and if I roll it. So, before I roll it, the x is the random variable based on the fact that what face will come out when you rolling the die. So, if it is say for example x, and it can be either 1 or 2 or 3 or 4 or 5 or 6, and when the actual value is seen by us considering number 5, we will say the realized value is 5. So, as I was reading the first point, so you collect a sample pertaining to a data set, and they would be regarded as the realization of the random value x, with which is we will basically have a probability law or a probability distribution or a PDF or a PMF, as the case may be, depending on. PDF would be the case when you have basically a continuous distribution, PMF would be the case when you have a discrete distribution. Usually P, the probability law, which we want to know, is specified with its cumulative distribution, as I said, which is the cumulative distribution function, and it will be basically given by capital F of x, and obviously all the properties which all the 4 properties which you have already considered in statistics should hold true when we are commenting about the probability distribution function or the cumulative distribution function capital F of x. And generally we will consider the x value, which is the random variable in the continuous case, to be lying between minus infinity to plus infinity. Generally f is not completely known, because if it was known, then alpha, beta, gamma, which I said as the scale, shape and location parameter, then obviously it does not suit us to basically collect some set of observation in order to conduct the study, where our main concern is to find out any of these 3 parameters or the combination of these parameters, which is alpha, beta, gamma. So, generally f is not completely known, and we are generally interested in drawing statistical conclusions based on some studies and based on some particular test. You want to basically draw some statistical conclusions about the parameters theta, which is basically a functional form of capital F, and based on the value of theta we will be able to predict or find out the functional form of capital F as better as possible or as close as possible to reality. When we are doing a parametric model estimation, the assumed functional form of F may involve some unknown algebraic constants, and this is the constant which I mentioned is alpha, beta, gamma for our case. They would be interpreted as the parameters which I told, and in generally for the normal distribution, the algebraic constants the parameters are basically given by mu, which is the mean, and sigma square is basically the square of the standard deviation, which is the variance. The objective in point estimation. So, generally when we do any inference test or inference testing or inference study, we basically have 3 steps. One is the point estimation, one is the interval estimation, and based on the point estimation, after the results have been verified using some prior methodologies, which are very simple to understand, at least for our course what we are going to deal with. Once this are done, we basically go into the concept of hypothesis testing. The objective in point estimation is to utilize the information in the given set, which is the set is basically I pick up a set of observation which is x1, x2, x3 till xn. These are the set of random observations, and we choose a particular statistic. Now, statistics is basically the actual functional form based on the sample which we find out. That means, x1 to xn whatever set of observation which we have, which we call a sample, and we combine them in certain form and some functional form, we find out a particular statistic. That statistics is used as a best estimate for the population parameter for which we want to do some studies. So, this is basically a statistic. So, sample observations and random variables are chosen to find out a suitable statistic. So, this statistic is a function, as I mentioned, of x1 to xn, and this n symbol is utilized to denote the number of observations you are going to take, such that the statistics Tn estimates theta, the parameter value, in a very meaningful way, and our main concern would be basically to be as close as possible to the estimate which is theta, such that we minimize the loss or minimize the prediction or minimize the forecasting error, whichever we are trying to do. In general, we have seen that in statistics we basically impose 2 rules. One is the consistency and the unbiasedness, and consistency means that when we are trying to basically find out the characteristics of that particular the estimate based on a very large sample size, it should be consistent in the sense that in the long run the overall variance should be as close as possible to the actual one, in the sense the actual differences in the variance from the sample should be as close as possible to 0, such that we are able to predict the overall estimate value of the parameter value as accurately as possible. That is point 1. And point 2 is that whenever we are doing the unbiased test, our main concern is to basically choose that particular statistic in such a way that in the long run, as we keep repeating the observations, considering n number of set of observations as chosen each time, the overall sample statistics in its estimated sense should be as close as possible to the parameter value which is theta, which means the expected value of T n should be exactly equal to theta in the long run. Obviously, if there are some difference, there would be some biasness, which for our case would be only true in the case of in advanced statistical studies, but for this course as it is DADM 3, which is more to do with operation research, we would not be going to that details. A good idea to choose an optimal estimator would within the class of consistent and possibly unbiased estimators would be very important for us, because once we are able to find the optimal estimator, our job is done and we can utilize that to find out or predict the actual parameter value. In the case we are able to pick up only one set of observation with the sample and we utilize the sample in order to find out the statistic, which should do our work. One idea when we are trying to find out a statistic based on the sample set of observation x 1 to x n would be to find a non-negative metric or measure, which would be given by L, the loss function L functional form, and it will be divided for all the overall domain space of T n. T n is basically the estimate which you are going to find out for theta. So, we will try to find out the non-negative metric L, which will be defined for all values of T n, where theta varies over the parameter space depending on whatever the actual realized values of or actual plausible values of, while T n would vary over the sample space. So, basically you have the overall space where you are trying to basically find out that in what range theta varies, and as you pick up samples there would be a sample space in which T n would basically vary. So, you will find out that you will try to find out that T n varies over the sample space, which is usually defined as a subset of R n. R n is basically the dimension of the sample which you are going to pick up. So, n number of observations is very important for us. As you increase n, obviously the statistic would be in the long run actually should be as close as possible to the parameter value. So, T n varies over the sample space, which is usually a subset of n, and in the case of the Euclidean space it would be of dimension n. So, let us see this graph. So, along the x axis we are trying to measure the difference between the statistic and the parameter value. So, if the parameter value is basically theta, in the statistic is theta hat, then the difference of theta hat and theta would be denoted by delta, and delta would be measured along the x axis, where any value, when I am basically trying to now highlight using this red highlighter, any value onto the right would be positive, in the sense theta hat minus theta is positive, that means you are overestimating theta using the value of theta hat, and if I go on the left hand side it will be theta hat minus theta would be negative, hence we are trying to basically find out the estimate of theta using an underestimated value which is theta hat. Now, the beauty of the graph is that consider that the fact that if the loss function on the overall positive and negative effect which you try to find out, considering that you have overestimated theta using theta hat or underestimated theta using theta hat, the overall shape of the graph would be a quadratic in nature. Now, why it is quadratic in nature and why we assume it quadratic in nature is that in the long run we will try to basically minimize the loss as far as possible. So, trying to basically minimize the quadratic equation would be akin to the concept that we are trying to basically minimize the variance, because what is variance? Variance is basically the expected value of, as we try to find out, and in the case that if there are n observations, it would be 1 by n, and it will be a summation of x I minus x bar x n bar whole square, provided mu is not known, and we basically utilize x n bar as the best estimate for mu, in the sense that we have already discussed that how you utilize the best estimate from the sample as a proxy for the theta value which we do not know. So, if you basically draw the overall loss function as a quadratic one, it will means that the penalties for both positive and negative values of delta, whether theta hat is greater than theta or theta hat is less than theta, it will be equally penalized. So, if I move 2 units onto the right or 2 units onto the left, and if I consider the quadratic equation is basically theta hat minus theta whole square, in that case we will say the overall loss which you will encounter, provided you have an overestimation problem or an underestimation problem, would always be the same, that is would be of unit 4, provided that you are not multiplying any constant value with theta minus theta hat whole square. And as I mentioned that few minutes back, trying to minimize the overall estimated value or the expected value of the loss function will be exactly equal to the concept that you are trying to basically minimize the variance. In case the loss functions you are using the modulus for loss function or mod loss function, in this case also the overestimation and underestimation would be equally penalized, but the interesting fact it would be that overestimation and underestimation would not be equally penalized considering the overall loss function is quadratic. In this case it will just be the mod of the difference of the estimated value and the parameter value. So, if I basically find out theta minus theta hat and I am trying to plot it along the x axis where it is positive onto the right of origin, which is this is the origin which I consider, and it will be positive onto the right of the origin. If I consider on the left to the origin, it will be considered negative. So, in that case here also the overestimation and underestimation for theta hat minus theta, whether it is positive or negative, would be of equal quantum. But the interesting fact is that as you are in and around the origin, there you will find out that concept of the differentiability would be a problem, because the rate of change of this function at the point 0 happens in such a way that it will be almost difficult to find out that what is the dy dx of this curve in case it is needed to solve our problem in more details. So, in this case you will basically have modular loss function. The modular loss function would be given by the value of mod theta hat minus theta. It looks interesting, but trying to basically solve it would be much more tedious than the case when you have basically the quadratic loss function which we just discussed. In case if the linear loss function, now this would also be true for the case of the quadratic loss function. I have not drawn it, but I will try to draw it using the graphs which you have just considered. I will come to that. Considering the loss function is asymmetric linear loss function, but is of the modular type, in the case that we will basically add or multiply some parameter values k 1 and k 2 for the case when theta hat is basically greater than theta, and if in the case if theta hat minus than theta, then we will basically multiply it by the factor of k 2. So, k 1 will be multiplied if it is overestimated, k 1 will be multiplied, k 2 will be multiplied if it is underestimated. So, if the k 1 and k 2 values are higher and lower, then overestimation will be more penalized on the right hand side and underestimation will be less penalized on the left hand side. In case if I just reverse the values, that means k 2 value is much higher than k 1, then the part of the slope of the red line, which is basically the underestimation, will be much more higher onto the left, and the slope of the blue line which is on the right would be much lower. So, with this I will end the 34th class and continue the discussion of the loss function, and then come to the estimation problem in the DA concept, where we will be trying to utilize the concept of linear programming in order to understand why DA is important and how it can be modified as a simple linear programming problem. Have a nice day and thank you very much.